record here. That way, the Twitch stream doesn't have to be pulled down. And you don't have to see my Isaac playing as part of your official lecture material. Yeah. I mean, if you, I hear that a couple of pencils and a rubber band works for a capo. Yeah. You know, I bought a capo a while ago with the pure intention of getting better at guitar, and I have used it once. All right. Okay. So, last time, do this so I don't hear myself in the room. We ended about here, and I believe that we had a whole bunch of children unhappy in the background, which happened. So now I'm in my fortress of solitude down here, which is actually my daughter's schoolroom. Good chance I'm down here for the rest of the semester too. We'll see. But we've got Link back there watching us, so that'll be helpful. Anyway, we left off talking about shaders, right? And this whole set of slides is going to be mainly about kind of the nitty-gritty of shaders. Just forewarning, it's going to be very bland and not super exciting today. But we're going to basically look into all the variable types, all the things that we can use to help us write shaders. And you're going to take that and apply it to writing your shaders in the future. So if you're looking at, say, like shader toys or there's the other one, GL, SL, sandbox, and you're going to see like all these variable definitions. You're going to see all these little attributes, which up until this point, you haven't given a second thought to because I've just been saying, hey, run this code, and you get a triangle. It's not super exciting, but these attributes that we're sticking on them have meanings, and some of them are semantic meanings, meaning, basically saying that it means something to the programmer, and some of them are very specific to GLSL. So we have to be careful how we use them. And again, we're talking to the GPU here, so we need to make sure that we are on the up and up with that. But left off here, texture mapping, right? So we're going to send different textures to our shaders. These are fragments, right? So we're going to have the same set of vertices for all three of these spheres that you see here, you know, if we were modeling this in WebGL. But the fragments would be different. You know, here you have a matte finish, here you have a reflective, here you have a bump mapped finish. Depending on how far you want to go into WebGL and GLSL, you know, you could get into this level of modeling. But honestly, if you're getting to this point, you're probably going to end up using a different tool. But again, it's kind of one of those things where if you want to do a web-based application, WebGL is a great way to go. One other thing I should mention too, so if any of you are looking to learn Unity or Godot or Unreal, and you want to do that handy export to web function that they all have, right, let me, this is a future demo, which God, I hope it's still here. Not that one. Dungeon Ball? This guy? Did I still have it up? Cool. So you can export in Unity to WebGL. This is something which we'll probably play around with later. But here I've got a little ball rolling around a 3D world. So this is, if any of you have played with Unity, there is a ball rolling tutorial. We will do that later on in the semester, is again, a forewarning of that. But this is all just WebGL at its core here. What Unity is doing and what Godot is doing is it's taking all of the, say, C# code or GD script code or, you know, whatever language you're writing it in. And is it F? I have a way to spawn enemies in here too. I remember what, it's been a while since I've touched this demo. Oh, sticky keys. Yes, I want sticky keys on. What's the key to get the enemies in? It's one of those. There, got a bad guy. Yeah, this lighting is from the Unity asset store. I put zero effort into it. But this is all just WebGL under the hood. Right, so if I look at the page source, obviously it's built from Unity, so it's going to have Unity bindings and all that fun stuff on there. But it's still just WebGL. Oh god, it's minified. No one's going to be able to read this. Okay. I've never looked at the raw JavaScript here. I just kind of thought, hey, they might be interested in seeing this. But it is, you can see from the code here, this is a WebGL container, basically. So if you do, let's say, build a game in Unity or Godot or something like that, and you port it to the web, you click export to HTML5, there's a good chance it runs like crap. And maybe you have to go in and do some optimizations. Now, yes, you do it in the engine, but having a knowledge of how WebGL works can help with that a lot. Ooh, somebody's got some scary script in there. Yes, love that JavaScript. Okay, so shaders is what we're talking about today. Not WebGL specific, as you have all kind of mentioned so far this semester. Shaders are, again, the buzzword in graphics because they talk to the graphics card and they take all the load off the processor. One thing I will say, so I was, slight diversion. I was bumping around Reddit earlier, and there was a post on game dev about using Pygame for a game programming language. I thought that was quite interesting. And absolutely use Pygame, use Python for your game development, but you're CPU bound in that case, right? You don't have access to the graphics card without pulling in other modules and things like that. And that's what shaders get for us, is it gets us right direct access to that massive matrix processing engine that we're going to come to know and love. So what are these shaders? Basically, they are common interfaces. They're basically programs that work with OpenGL, work with DirectX. If you've played with DirectX, I know at least one of you have. And it really, was it? Oh, dear God. Civ 4 is now is it scripted in Python or is the graphics in Python? Would be my question. Because I know a lot of games will do a scripting engine and use something like Lua or Python or something like that. But the graphics will all be in OpenGL. Okay. That's one common thing too. So if we ever go down the game development discussion path, your graphics are going to be in something very performant, like a C or a C++ or Rust or something like that. And then the user bindings or the things that you give to your game designers or your graphics or your art department, you give them an easy interface. Maybe it's, Python or Lua or something like that. Anyway, so shaders are, and we've talked about this already, it's using GLSL, so that's your OpenGL shading language. Basically, it makes life a lot easier for us. C++ for the engine, Lua Python for the scripting, plus shaders, yeah. One of the games that I honestly haven't played this in several months, kind of intentionally. I used to be really big into a roguelike game called Dungeon Crawl, Stone Soup or DCSS, and everything is in C++, and there are basically how the maps are generated and how all the characters interact, that's all in Lua. So even like simplistic tile-based games without a lot of animation will still do something similar. Yeah, we can go down a whole discussion of game development. That'd be a lot of fun at some point, but takes away from GLSL, unfortunately. So GLSL, this is our shading language. It is very C-like, as you have seen so far, right? That Vertex shader, Fragment shader, they look like C++. It is different than C and C++. So some of the things that we're going to look at today are going to show you how it's different. But if you know Java, which all of you do know at this point, right? You're all juniors, seniors, if I recall correctly. You should have no problem with this. And actually, there's some abstractions in here that make life easier as well. So C-like, you have matrices, you have vectors. Java, yes, just like the coffee. Absolutely. That's exactly what we're talking about here. And then I don't have any bad dad jokes for what JavaScript is. Especially since you're all writing JavaScript. I could make some fun puns about that, but we'll save that for another day. Anyway, so you get matrices, which are, 2D arrays basically. You have vectors, which are 1D arrays. Samplers is something we'll talk about a little bit later. Those are basic ways of representing textures. So we're going to define vertices, we'll define fragments, and then our textures that we're going to slap onto polygons will be basically in samplers. If you are backwards porting anything, so maybe you want to support an ancient system, just be aware that if you're kind of going back in OpenGL versions, once 3.1 rolls around, you need a shader. It's not a option. You need them after this point onwards. So be aware of that if you're going through different versions of that. Okay, you're going to see a lot of code snippets in here that are very familiar. Basically, we're going to be explaining them in a little bit more detail today. So this is our simple vertex shader that you have come to know and love by this point, right? It is a pass-through shader, right? Because there is nothing going on here. We are just passing information on. But the things we haven't really talked about yet are what all these things mean here. So attribute, this means that we are getting input from our application. And if you remember, application is what we call that JavaScript file. The shaders that you write are actually like one of the last steps in the pipeline before they go off to the graphics card. So you have your HTML file, you define your shaders, and then you define your JavaScript application, but actually the JavaScript's getting called first. Now the shaders are being compiled, at the outset. It's part of basically the browser's organizational procedure, but we don't actually access that until we get into the application. And I've got a little flowchart in a little bit that will help you kind of visualize this too. So if we put the attribute tag on there, we are expecting this variable to be accessed in the application. Going back to one of your questions on the homework assignment, right? Let's see. Hopefully I don't have anything horrible in my history here. Up, up. A little bit farther up. Okay. It's kind of a interesting line to talk about since somebody asked about it. var vPosition equals gl.getAttrib location program vPosition. So this is in our application code, right? So this is in JavaScript. I'm telling you, if you see this attribute moniker here, this decorator basically, it is an input from the application. If you look at this line, we are linking our application to a shader variable. So there is a linkage that is happening. An attribute is telling us that. We are telling WebGL, expect something to happen here. Right, so that's basically what attribute gets us. Notes, come back, please, so that I know where I am. Thank you. All right, void main should make sense, right? It is your main function. Looks very C-like at this point. This position variable needs to be the same name in the application as it does here. Otherwise, there's going to be a mismatch. You're going to get a compiler error, and it's not going to work. All right, so make sure this matches what you're pulling up in the application. If I change this name to vPosition underscore, I don't know, cube1 or something like that, maybe I have a bunch of objects I'm going to keep track of and I need multiple positions. That name has to match. Or I rename it to something a little bit more exciting, v pause. So I want to be lazy in my writing. Right, make sure it matches. This other one, I mentioned this before too, but just to really hammer the point home, gl underscore position, this is a built-in variable. The GPU, or sorry, the shader is expecting this to be there. This variable is going to be what is passed on to the GPU for rendering this vertex, basically, or whatever vertices are coming in. So things have meaning in here. We're not just slapping attributes, or sorry, we're not just slapping decorators and types on there. One other thing you see here too, vec4. This means we have a four-dimensional vector, and it's going to be in floating point format, is what we expect with this. We'll talk about the different types momentarily too, but just since I don't have a line there. Makes sense though, right? Other thing here too, we expect main to be a void. We're not returning anything, so void main, nothing's coming in, so no parameters. And here we have our execution model. So I pulled this from the book. If it were me, I would draw an arrow going into application program so that we know where we're starting. But basically here we're showing that the application, that JavaScript file is the starting point. Okay, so JavaScript gets executed on window.init. Things happen in the application, right? You do your setup, you set your context, you link variables to the shaders, and then later on, you call gl.drawArrays when you hit that render block, right? Do you need render? Not technically, but it's kind of nice to abstract that out. So two things are happening here. We have two lines going out of our application program. We are linking our vertex data to our shader program to our GPU. So when we are calling those 6 lines of code, 6 lines for now, it'll get more complicated later on, I promise you. We are saying this is our vertex array, this is our fragment array, These are the variables we are linking to. Make sure that we have proper variable linkage. If we don't, you'll get compiler errors or JavaScript errors. Either you're going to get a pop-up because there's a shader issue, or you will get a JavaScript console statement saying you done effed up at this line, fix it. Again, if you're struggling with any code whatsoever, check your web developer console. Works in Firefox, works in Chrome. I am not bothering to try it in Edge, but I can guarantee that it's probably in there too. So, application program, that's where we start. Next thing that happens, we call gl.drawArrays, right? And if I pop over here to actual code, let's look at our gasket, for instance. Right, here's where we are doing that branch off into our GPU. We're linking to our shader, we're linking variables, and then we call render. And again, render is where we will handle animations later on. We'll do a callbacks for render to be always called. But here's that gl.drawArrays function. This is the function that says, okay, Vertex shader, it's your time to go. From then on out, we are done with our application. The Vertex shader is going to do its processing. We're going to get vertices out. We'll get into some kind of an assembly. And then after that, it's going to go to the fragment shader, right? So that's basically our pipeline here. That sneeze is not going to actually happen. Okay, so application to Vertex shader. Once you leave the application, and let's assume that your Vertex shader and your fragment shader are simplistic, you really have no heavy lifting to do. This pipeline in WebGL is going to handle it all for you, which is really kind of nice. So we have our Vertex shader. Now we're going to get into our fragment shader. And right, again, very simplistic at this point, but we have some pieces here to look at as well. GL frag color, also a built-in variable, mentioned that many times as well, but basically this is the color that is going to be whatever your shapes are. So if you just pass in a single color, everything will be that color, right? By setting this frag color, we are saying this is the object that's going to be painted on every single vertex. And if we only set a single color, that single color is going to be applied everywhere. We're going to look at the gradient shader again in a little bit, but if we wanted to make this an a per vertex type of coloring, we would send in an array here, right? We're basically going to pass in a variable that the application will be setting later on. So be aware of that. And again, vec4, we're expecting floating points here. You might recall last time that I was setting these to also be like 255 and 0, 0, 128 or whatever, messing around with these values. It will accept integers, but that's kind of getting into the semantic side of things where this should really be an IVEC for if we want ints effectively. So you have that. Again, void main, no return type. Here we have precision medium P float. So we're going to talk about this in a little bit, but you're setting the precision of your application. And I remember asking you about this last time, so I'm not going to do that again and ask you the same question. But precision is going to be how much, basically how many decimal places do you want to handle, right? How precise do you want your calculations to be? If you have a fluid dynamics simulator, you need a ton of precision, right? You need all of that information. Most programs, you're probably not going to need anything beyond medium. With that, the actual machine that you're going to be running this on is also going to be limited. So if you're, say, running this on a potato, to use a common term, if I'm going to run this on like a Raspberry Pi, an old Raspberry Pi, or if I'm going to run it on an old PC, and I want to set this to, say, high precision, it's not going to work. That's just not available for that architecture. So if you are getting into the realm of needing very precise calculations, we're going to have to add some extra checks in there to make sure that the system supports it. Probably the first time you're going to see that WebGL isn't supported everywhere, but we'll get into that in a little bit. So simple fragment shader, again, just pass through. We're not doing anything other than setting a color here. Right, so basically I'll review for you so far, just kind of contextualizing. Okay, moment to hydrate. Now, moving on to this execution model. Again, this view that you see here coming into the rasterizer is basically the output of the vector assembler. Okay, question. So for the gasket program, we're calculating vertices on the CPU, storing them in a buffer, then the GPU executes the shader code for once for each vertex in the buffer. Is that correct? Yes, that is correct. Absolutely. Perfect understanding there. So if you are doing something in JavaScript, it's being done on the CPU, basically, is one way to look at it. If you are doing something in the shader, it's being done by the GPU. Some of the later examples, I want to say it's either the last gasket in the chapter. Actually, I've got it up here, I think. No, it's still just a pass through. Once we get into chapter 3, we start doing like animation and stuff like that where things are changing. Yeah, we're going to start doing more shader-based stuff. Yeah, but JavaScript, CPU, GPU, shader. Okay, so coming out of this Vertex shader, we have our primitive assembly, if you remember, which is just effectively our polygons. So we have vertices, like if we have one triangle, 3 vertices. This is now an assembly. And this is all inside of the pipeline, right? You have nothing to do with this at this point. You write your fragment shader. The fragment shader is going to take in that assembly. It's going to rasterize it, which again is basically going to be, well, the assembly is also going to handle clipping, right? It's not going to draw things that don't need to be shown. We're going to have our list of vertices, and then we're going to turn them into fragments. And again, the rasterizer is basically saying, okay, you're going to get these pixels in this particular location. We will then color them, and that's going to take input from your application, right? So the rasterizer goes into the fragment shader. Fragment shader takes info from the application, which is linking that whatever variables you're setting to that GL frag color. That then goes into the frame buffer, which then gets sent to the screen. Make sense? Hopefully. A lot of words, a lot of hand waving, a lot of follow the lines. But this is basically our pipeline, our WebGL pipeline kind of broken up into this is what the Vertex shader does, this is what the Fragment shader does. Good so far, I hope. Yeah, I love saying your username's Kitten Mittens. That was a good question. Okay. And I mentioned clipping too, right? We don't want to show things that don't need to be drawn. That's just wasted CPU, GPU cycles. So it's going to be clipped, yeah, right here. And that's something that we'll look at in a little bit too. A little bit being a few lectures away. All right, data types. Most exciting thing in your entire academic careers, I'm sure. They're very C-like, again. So we have ints, we have floats, we have bools. So pretty much straightforward data types coming out of, say, C. Precision of these variables will depend on what precision you set. So is your the 32-bit, 62-bit architecture, that will have input on how we set these things. Excuse me. We also have vectors. So if you are in the C++ realm, you have the benefit of having the standard library has vectors. I know all of you are Java users, so you've seen vectors before too. They're just one-dimensional arrays with extra syntactic sugar on them for like adding and getting length and fun stuff like that, right? So we can have them as floats, 2-dimensional, 3-dimensional, 4-dimensional, just meaning we have 2 spots, 3 spots, or 4 spots since it's a vector. We can make them integer-based. We'll call them IVEC. Booleans, we'll call them BVEC. So instead of float vec2, it would be IVEC, basically. So IVEC2, IVEC3, IVEC4 if we wanted. Everything that we're really going to be doing is probably just going to be straight up floating point vectors, unless you're doing extra stuff. All right, we also have matrices. So again, 2D arrays, 2-dimensional, 3-dimensional, 4-dimensional. They're referenced in column major format. So basically, if you want to access an array element, it's going to be referenced in this particular fashion. So if I define, say, mat2, or sorry, mat3, I've got like a 3 by 3 array, it would just be first it indexes on the row, then indexes in the column. So I'd be going, say, down 1 over 1 if I wanted to reference something. And since this is a reasonable good language, of course, they're indexed starting at 0. All good languages start at 0. Fight me if you're a MATLAB person. Other things. We have constructors. So Bear's kind of mentioning that this is different from C. C++ constructors are a little bit different. We can initialize them, say, in this way. So I'm going to define a 3-dimensional vector with a 3-dimensional vector. Then I'm going to create a 2-dimensional vector and instantiate it based on this 3-dimensional vector, and it's just going to lop off that last spot for us. If you tried doing this in C, it would really complain. So we are kind of getting into a little bit of difference in terms of how rigorous, I guess, the language. I was going to use the word anal, but that's always fun to say on stream. But a little bit loosey-goosey, I suppose. Terms of service, there we go. All right, pointers. Got to talk about C and C++. We have to talk about pointers, right? And how stuff is referenced. No pointers here. We just copy back and forth. So everything is considered a basic type. So we're just going to pass the whole thing as we go. So you can pass a struct, you can pass a matrix, you can pass a vector, and you can just use it as is. So no pointers to worry about here, which is nice. Makes life easier. Okay. So the qualifiers, this is where things get a little bit, we're going to actually use some of these terms now. So matrices, vectors, fine, read the user manual and you could get the exact same info I just gave you. But qualifiers are where we start telling WebGL what these variables are supposed to be doing. So basically this is going to help our shader understand what our programs are doing. And we're going to tell them how these variables are changing. And this is something the shader needs to know to function properly. And the reason why is that based on how these things are changing, is the primitive changing? Again, the primitive is a collection of vertices. Is the vertex changing? Are the fragments changing? Is the application changing things? The shader needs to know all this to function properly. Basically, when we have our application feeding data to our vertex shader, I know I forgot the word, I've been using it all lecture here, an interpolation has to be performed, which is basically just finding, a value in between multiple values. You think of that gradient shading that we're getting like a nice smooth transition. Things are being interpolated. You may also see the shorthand lerp. That's a short way to say interpolate. Basically, you're just finding a value in between two values. The shader is making these calculations for you. You're doing some lerping in your homework by finding the bisector in those triangles. You're finding a value in between. That's what that mix function is doing, basically. Okay, so the qualifiers. Enough preamble. Let's talk about them. Attribute qualifier. So this is one we talked about. You need this in your application to link up to your shader, right? These are allowed to change at most 1 time per vertex. So if you have an attribute variable, it changes once each vertex. And again, we can define multiple things for these, right? They can be floats, they can be vec3s. They link up to a shader, but they're going to change at most once per vertex per iteration. Okay, so it can change, if you have like an animation loop, they can keep changing, but it's only changing once. And what you're going to see too is that we're using GLSL1. GLSL2 is going to use the in and out decorators instead of attribute. Just be aware that if you start going out and looking for tutorials, you're going to see in and out in some of those shaders out there. And by default, we're using GLSL1. I don't know what the exact headers you need to put into force GLSL2, but it's not fully a standard yet, is my understanding. I think it's at the proposal stage. Okay, so we have attribute. We've seen this. Uniform, we really haven't seen this one yet, so something slightly new for you. This is a constant, so it's a uniform, it's never going to change. That means that for that primitive, wherever it is, it's going to be the same. You can change things in the application, though, which is kind of an interesting little spin on things. Basically, once the Vertex shader has created its primitives, right, these collection of vertices, these polygons that we're sending to the rasterizer, it's set in stone. The fragment shader is not changing these variables. The vertex shader is not changing these variables. Okay. So effectively, the application can change them. And if you look at the rotating square example, you're going to see that there is a theta variable. I looked at it last time. That's a uniform. Application's changing it. Vertex shader is not changing it. And this is basically a const, for lack of a better word in this kind of domain. It can change, which breaks common const. Basically how we handle consts, right? They don't change at all, but the application can change them. Did I close this? I think I did close it. Let me show you this super quickly. So this is rotating square in chapter 3 in the GitHub page. We have a theta variable. Theta is going to be our, basically it's how we're calculating this square rotating. If you remember, it was just kind of spinning about on its center axis here. It's defined as a uniform. It is not being changed at all by the shaders, right? So vertex shader, we're taking it, we're doing sine and cosine off of that, and some simple multiplication and addition here, but we're not changing this variable. Application is changing it though, because we are actually updating it in our render function. But again, since it's uniform, that's fine for the application to do that. So again, things to be aware of. If you set a uniform variable and you try to change it in the shader, you're probably going to have issues. All right, so next one we've got is our varying qualifier. This is going to be something where you pass a variable from the vertex to the fragment shader, and every single thing that we're going to pass between them needs that varying designator. And again, newer GLSL is going to use out and in for this. So let's say that we have a vertex and a fragment variable color that we want to play with. Right, maybe we're defining it or maybe setting it in the vertex shader and passing it to the fragment shader later on. It's going out of the vertex and into the fragment shader. We are not doing this, just again, something to be cognizant of. We're just going to call it varying. Now, what this means to the shaders are that automatic interpolation is going to be happening here. So again, we are trying to basically interpret these values as they are transformed as we go. So some automatic warping is going to happen here, right? So we're going to use varying. You've seen varying already quite a bit too. Shaders. Where was my shader example with varying? There we go. We've been using this as our V color. All right, so if you look at gasket 3, we have a varying variable here. We're defining it in our vertex shader. We're doing so. Okay, gasket 3's got some fancy stuff. Forgot about that. But basically, it's being updated in the vertex shader, being passed over to the fragment shader. Again, you see varying. We set it to the built-in color, right? And if we remind ourselves on what gasket 3 is, that's this guy. It's kind of a pixelated pointillism, whatever you want to call this particular style, but colors are changing. And again, because we are updating in the vertex shader, it's being handled by the GPU there. So, varying. Linking variables between shaders is kind of the TLDR there. All right, so recap, we have we have uniform, we have varying, we have our attributes, basic 3 qualifiers that we care about, at this point in time. We do also have some naming conventions as well. You should be aware of naming conventions from your various programming classes. These are not required, but they're very helpful for you and for other people reading your code, namely me or project team members if you decide to work on a team later on. So if something's being passed to the vertex shader, start it with V for vertex, right? So the application variable should start with V, shader variable should start with V. This helps you understand this application variable goes to this vertex shader, they're the same thing. If it is a varying variable, it should start with F in both shaders. So if you have a variable that's in the vertex shader and the fragment shader, because it is varying, start it with F. And they have to have the same name. So we've seen this F color variable before. You might have thought, oh, that's weird, they have the same name. This is why. It's varying, and it's used in both places to make it F. If it is a uniform, nobody cares. Name it whatever you want, but just make sure that you follow, your own conventions, right? So if you're going to start it with lowercase u, that's fine. If you just want to leave a designator off of it, that's fine too. Just basically be consistent in that case, but uniforms are less important than varying and shared variables. But just again, convention, not strictly a requirement. Alrighty, any questions so far? How are we doing? Big info dump for all of you, so it's not always the most exciting. But obviously good to kind of understand all these variables that we're defining here. Alrighty, doing okay. Yeah, and that's why we're going to be doing lots of labs with this stuff. Kind of why I gave you the gasket lab before talking about a lot of these details, because you've done a little bit of practice. In the next one, you're going to be doing some animation, so you're going to see a lot of the same stuff. We're just going to kind of build onto it. So we're going to start rotating and looping things, and it'll become more clear, if it's not right now. Alrighty, here's our vertex shader. It should look very, very similar, right? Again, shaders are going to be mostly boring, which is great. That means that it's not that tricky to really understand. We will start doing fun stuff with them, though. But we have examples of everything going on here, right? We have attributes, we have varying, we have built-in variables, we have extra variables that we're passing in, and you see our convention of them being varying. These are defined in the vertex shader. We have an attribute that we're linking up to our application, four-dimensional floating point vectors. So if I look at this application, let's say one of you gave me a program to debug because you screwed it up and you need help, which is fine. I'm more than happy to help you. I can look at this and say, okay, this I need to look in the vertex shader for. This is going to be linked up in the application at some point. This is some common variable that's probably going to be changing colors because it's in everywhere and it's a color related variable, right? I can look at this stuff and see what's going on, and so can you as you go. Fragment shader, same thing. Again, beating a dead horse with this pass-through shader at this point, but again, the more we use it, the more we'll get more comfortable with this kind of stuff. So, built-in variable, shared by both shaders. It's varying. We know things are going to change. Medium precision. We'll get there. Okay. And a couple of other points here as well to really talk about. So here are the magic 6 lines of code for sending data from our application to our shaders. Right, so these, you basically have them in groups of 3 and 3 here. So the little magic thing, and again, I'm going to repeat this because I mentioned it last time, but this is something I struggled with when first really digging into WebGL, coming from an SDL background and a Pygame background really, is that this buffer that you create at the top here, this is what is going to be tied to the next 6 lines, right? So you say var c buffer equals gl.create buffer. You bind that buffer to gl.array buffer. And this effectively is saying that this is your gl.begin and gl.end. So I'm starting a primitive, and then I'm going to end a primitive in a little bit. But this is basically tying one object together here. So here I'm flattening some colors, right? So I'm sending a list of colors to a buffer. The buffer is going to be packaged up and sent to our shaders. Static draw, nothing's changing. right? And then here, this var v color, again, there's that v, the convention is there. We're going to get the v color attribute from our shader, bring it into our program, or actually it's more link the program to that shader since we're going that direction. We're going to very clearly tell the shader, okay, this is a v color, we've got 3 dimensions, it's floating point, and I can never remember what these last 3 parameters are, and I have to look them up every semester that I teach this, but they're very rarely used beyond the basics unless you need basically to set some extra vertex information. And then we're going to say, hey, link that v color variable up to our vertex array. And then we basically have a primitive represented in JavaScript code that is going to be sent to draw arrays. Talked about this uniform variable too. I showed you that theta in terms of things spinning. You can also say set a color as a uniform variable, right? It's not going to change. In the application we can change it, but that's fine. So vec4 color, so this is going to be red. And then I'm just going to have a uniform variable called color, right? So here's uniform vec4 color. This is in my application code. Create a color, link it up with our fragment shader color, and then set it. So gl.uniform4f, this is basically the equivalent of enabling our vertex array, except here we're just setting a uniform to our shader. Again, the important kind of takeaway here and where this might be different from standard procedural basic graphics drawing where it's all CPU bound, you are linking them. Hey, thank you for that. Normalize cast to float. That's right. Okay. Yeah. So we've got a specific definition of the extra parameters there. Thank you. Yeah, those are ones that I have never really had to use myself too often. But if you do need them, right, then that's going to be the thing that you have to look up. Yeah, exactly. Yes. Yeah, that's why I said we can, unless you need to do something kind of off the beaten path, you're probably never going to need to change those. So yeah. Thank you for that. Okay, so makes sense though here, right? Application, set the uniform, pass it to the shader. Shader just handles it. Okay, so that is the kind of the details of some of our decorators that we've been kind of pushing off until later. Later has happened now. I already showed you how to send color arrays. I just want to kind of go over that again, and I forgot to do this last time, so let me make a quick note. Basically, I'm going to show you a demo where we have a shaded triangle. Basically, what I like to do, at least for all of you, is to give you different examples of things that you might want to do. So this is going to be per vertex colors. And again, we have seen this already. You know, I did the example, I think, with the square before. But where are you at? In there. Okay. This one is not up on the GitHub account yet. Should we open the correct one? This is no longer CIS or CSI 4900. Where are you at again? Can I just open you from here? Yay, there we go. All right, nice gradient triangle, right? So this is not standard 4-dimensional vector being passed into our fragment shader. Looks easy, but a couple things we have to talk about here. We have to set up an array of these colors, right? So we're going to have a vertex array. We're also going to have a colors array. I showed you this, right, before? Please tell me that I'm not completely losing my mind. Maybe? Okay. Possible. The key here, and let me just kind of introduce this and I'll run through the code again just in case. And if I forget, I want to put this up. I'm going to put this up in the GitHub and on the Blackboard page. This vertex is red. This vertex is green. This vertex is blue. Those are the only colors I have set here. Right, this beautiful kind of nice gradient shading is automatically happening because of WebGL's interpolation routines. Right, if you remember last time we talked about excuse me, we talked about shading and whether it's flat or continuous. You know, this is that nice interpolation happening here. But if we wanted this to all be one color, we'd have to set all the vertices to one color. Or we'd have to do some tricky math to basically make sure every single face is one color. So let's look at the code for this guy here. I'm not going to run through it because I'm fairly certain I did this already. If not, that's fine. So, a couple of other things in the past. I think you did too. Okay, yeah, that's good. So in the past, this has been our approach for sending colors, right? Just set a four-dimensional array, or four-dimensional vector, sorry, of a color in the fragment shader. Here what we're going to do is, I've just got it commented out, but it's going to be a variable. That variable is varying, so we're going to make it start with lowercase f. It's a varying vec4, and we're just going to pass that in, right? In the fragment shader, or sorry, in the vertex shader, we're also going to define this variable. It's going to have the same name. They're two separate programs, remember, so we're not like overwriting or we're not getting into the space where we have two things with the same name. These are separate applications, right? So these would be separate files. They're compiled separately. We're just naming them the same by convention here. So we're going to define this varying vec4 fcolor. We also have an attribute vec4 vcolor. So this is where things get a little bit kind of wonky, iffy. Basically, this vcolor I'm going to set to fcolor. Fcolor I'm going to set to GL frag color. So I basically have a level of indirection happening here. If we recall, attributes coming from the application, right? So this variable is going to be set in my application. I'm going to pass that value to something that these shaders are going to do, right? So vcolor is from application, fcolor is shared by our shaders, fcolor then sets our GPU specific built-in variable. And what this fcolor is going to be is just an array of vec3s, is all it really is. But again, slight indirection. And the other thing that's happening here too, don't forget the application is running first. So the application, which I'll show you in a second here, is packaging up this vcolor array, sending it into our vertex shader, which then passes it to our fragment shader, which then makes the fragments, which then goes into your buffer and onto your screen. All right, so that's what we've got going on here. Now, in this JavaScript application file here, I'm going to create a three-dimensional colors array, and we're not going to set alphas here, and actually just for funsies, let's see what happens if I make this a vec4. So I don't honestly remember why this is a vec3. I wonder if this breaks everything. This local. Ooh, we get different shadings. Intriguing. Why is that, would you say? Interesting. That's not doing what I would expect it to do. Yeah, it might be a different order. That shouldn't be pink. Why is that doing that? I'll have to, let me think about this one rather than doing it on the spot. That's what I love about live demos is that they never go how you think they should. Well, why aren't you going back now? Oh, still vec4. Okay, there we go. Yeah, it's probably a different order, is what it is. Alrighty, so triangle. So I'm going to define my colors array. Now, the way this is set now, I have three vertices, I have three colors. I could do this in multiple ways. And yeah, I did this for the square last time because I made this a six-dimensional, or a list of six vec3s, because we had those 3 and 3 sets of vertices now that I think about it. I can make this as many as I want, right? I could define all the colors that I want in my program, and then I just index into this array when I want to set a vertex, right? So I could say, let's see, further on down, oh yeah, that we'd have to get into some extra code in here. But I think what happened last time was that I had a extra array of colors that I just pushed a bunch of specific colors in per vertex and then it was flattened. Here we're just doing it all at once. But again, everything's here the same. Configure WebGL, load our shaders, use our program. And here is where things get a little bit different. So first things first, we have these 6 lines. Again, the same that you've seen before. These are setting our vertex array. We're talking to our v position variable, but now we have these 6 extra ones here, right? So I'm going to create a color buffer, C buffer. You can call it whatever you want as long as the variables match here. I'm going to flatten the colors array, and I'm going to send that to my array buffer. The thing with array buffers in WebGL, again, whatever is in the array buffer at this time is getting sent out. So first thing, we are flattening our vertex array, sending it to an array buffer. Then we're flattening our colors array and sending that to an array buffer. And gl.draw arrays is just going to take one big happy buffer and index into that based on where we say our vertices are, where are our colors. And then it's going to do its magic interpolation to figure things out. But the key here and how we link it up is this get attrib location vcolor, right? So we were saying application, send this to that vcolor variable in our shader. So here's vcolor, here's vcolor. Remember, vcolor goes to fcolor goes to frag color makes it nice and pretty. I could do this. So right now we have a 1-to-1 relationship vertex to color, right? We are in theory duplicating a lot of information with this, which is not necessarily the best thing. There's a lot more intelligent ways we can handle that, and we'll do that later on. But one vertex, one color. That's one way we can handle it here. So this gets you away from these static colored images. You can basically pass the color along with it as you go. Make sense? I'll throw that code up and make it available to you if you want to start doing stuff like this. I mean, you could have this be you could draw whatever pretty polygon you want, right? I can make this like a clamshell. I could draw a faux 3D cube with just triangles and setting specific vertices. And I could color it however I wanted based on whatever colors I pass in. As long as the lengths of the arrays match, it's happy. Right? If I, again, muck with the vertex location, let's change this to 0, 0.5. Then we get a short guy. It's like that short Keanu. And let's make this a little bit of a different shade. Yeah, we can play with colors. We can play with sizes and shapes. Again, it's all triangles all the way down. So don't just have to do a straight up pass-through shader. I guess while I'm kind of mentioning that, not to go off too far off the rails here, but it was gasket 3, I believe. Right, so this was that other pretty gasket. I've got it open. Why am I going to there? Elderliness takes all of us at some point. So this particular one also looks, looks pretty nice, right? Nice kind of gradient going down here. This is actually supposed to be a 3D representation. This shader is doing some calculations in here. So vcolor is not an attribute, right? It's not being set in the application. It's actually being handled directly by the shader. And we've got some kind of nifty math going on here with basically swizzling and another term that we'll talk about very soon, where I'm indexing into this this 4-dimensional vector here. I'm calling the XYZ parameters and dividing them by 2. And I'm adding them by 1. And I'm basically doing some kind of nifty little, I'm not doing it, the book author's doing it, but a little bit of math trickery here. And the shader's handling this, right? The application's not doing this part. But we know that because it's varying. It's not an attribute, so we don't have to worry about it. Ugh. Swallowed a something or other. Anyway, back to shading. Oh, good, we're here already. So this is going to, if you're anything like me, and I'm sure all of you are not, this is going to look absolutely horrible to you. I'm not one for matrix math. I've made no, I don't feel bad about it. I'm not proud of it because it's something I should really know. And, based on all the math I've gone through, I should know it by now. But, if it's something that just doesn't stick with you, again, we have libraries to help you out with matrix math, right? Not everybody is great at it. But what do you have from a WebGL perspective, from the shader perspective, that can help you here? Right, so we have our standard trig functions, sine, cosine, all those fun ones, basic arithmetic functions. We also have normalizing. We can get our length of our variables. We can reflect them, which is basically it's a vector-based calculation. These are all available to us, which is very handy. We don't have to go through and do, a lot of the math that we'll probably draw out at some point and look at it. We can do matrix multiplication natively, which is great. So let's say we have a 4 by 4 matrix. We have a 1 by 4 or 4 by 1. It's column matrix, so 1 by 4. Or no, 4 by 1, damn it. We have our one-dimensional vectors here. We can do multiplication without having to do any magic transposition or loop through our vertices, loop through our arrays, loop through our lists. Basically, it's just handled natively. So if you have a 4 by 4 multiplied by a 1 by 4, you get a 1D array out of it. All right, this is handled natively, which is great. We also have these two new terms, which are going to be a lot of fun to say. We have swizzling and we have selection. And these are two terms which are probably not going to come up too much this year. We will talk about selection mainly in the idea that we can assign names to matrix elements or to array elements that make sense to us. And it's going to be very handy for you to quickly look up parameters. So let's say that I make a vec4. I can call it, let's say it's vec4 position, right? I can say position.x and get the x coordinate. I can say position.y and get the y coordinate. W we'll talk about later. That's part of some of the matrix math that we have to deal with, more camera related later on. I could also call it RGBA. I call it STPQ, where STPQ is more of a texture specific thing that we'll talk about later. But you see XYZ, you think position, right? You see RGB, you think color. The interesting thing about our shaders is that they're all the same programmatically. So if we have like a vector A dot B is the same as A dot Z, is the same as A dot P, is the same as A bracket 2. So these are basically all the same thing, just your programming context will call it differently. And again, this is meant to kind of help you out, make it easier for you to look up various parameters rather than saying, okay, A bracket 0 times, sine of A bracket 1 and trying to remember all of that fun stuff. You can just give it a shorthand name. And this is natively built into the language. So kind of helpful. Swizzling is another thing, which is something that we're not really going to get into, just as a forewarning if you were super excited about learning about swizzling. It is a fun term. Effectively, what it does is helps us rearrange vectors. So if you have a vector or a matrix, and I were to swizzle it, I'm going to rearrange where things are in that vector, for instance. So let's say I have two vectors, vec4s here, vec4a, vec4b, and I'm going to say a.yz equals this vec2. So I can basically just kind of muck about with the parameter locations. I can, basically what we're doing is we are rearranging things to make it easier for the GPU to render quicker or to perform calculations quicker. And I'm kind of intentionally not going into this in a super great amount of detail because it's a little bit beyond where we need to be here. And depending on the GPU, you might need to do different swizzling operations, and a lot of this is going to be handled natively, honestly, at this point. but it can help with making things go faster. Maybe your calculation needs a particular vector to be in y, then x, then z, then w order. Maybe it runs faster. There are specific algorithms and reasons why we would do this. Again, slightly outside the scope here, but if you look into graphics, you are going to see the term. And if it comes up, I don't think it's going to this semester, but that's effectively what we're doing there. But kind of the key takeaway is that our shaders kind of let us do little magic manipulations to our matrices. So let's say I want to swizzle this thing or select various parameters here. Or yeah, swizzling. And I've got a 1, 2, 3, 4, so a vec4 stored in this variable a. And I want wwxy. If we remember w is the last parameter, then we have basically it's x, y, z, w. So what this particular operation is going to do is it's going to take your vector and multiply it by the corresponding 4D array that gives you these parameters. Right? So here, effectively, either our shader or our JavaScript library, depending on where we're doing this calculation, is going to automatically do this matrix math for us. And if you see something like this, you're probably going to be doing it in the shader, honestly, because that's, again, why we have GPUs. They're really good at matrix math. But again, not necessarily something we're going to be handling right now. Just be aware that this is a capability that we have. Alrighty, 10 minutes left. So let's talk about our primitives. Hey, look how pretty that primitive is. Finally, the long-awaited formal definition of what we can do in WebGL. It is a lot more limited than what you would expect coming from an OpenGL world. I know, right? Those are triangles. Are you getting excited for your debut? We have a special concert appearance happening in the Discord chat. I believe right around the time class ends, if things are gonna work out okay with hiccups and all that. But let's get through class here and then we'll get to that. So here are the primitives that you have available to you in WebGL. You have points. Going to be x, y, possibly z coordinates in space. So it is just a pixel. We can set lines. We have a starting point, we have an ending point. So if I'm going to draw a bunch of GL lines, right? Maybe I want to draw singular lines. I need a starting vertex and an ending vertex. Basically, I need pairs of 2. We can do a line strip, where you have a starting point and then everything after that is connected until you get to the end. Right, very similar to our triangle strip, we have a line strip. You have a line loop. It's the same thing as a line strip, except the starting and the ending vertex are connected. So you basically end up with a closed shape of some point. And then the triangles we've seen already, right? The triangle strip we are basically adding on based on the prior 2 vertices. Triangles we know at this point. Triangle fan, just as a reminder that root vertex. So let me get a good cough in here off. Swear, getting old, say B. But your root vertex there, which is your first one, basically all of your triangles are going to be drawn from that point. We've seen the triangles. The lines are slightly new at this point, and the points are too. But this is everything that we have available to us. If you're coming from the OpenGL domain, and I know at least one of you are, you might be asking, hey, where's the quad strips? Where's the polygon? We don't have those here. Sorry. And that's actually old OpenGL that's been dropped as well, I believe, in new versions too. But depending on what you want to draw, remember, and again, we've talked about this multiple times and I've really tried to highlight it, but in your gl.drawArrays function, that's where you say which particular primitive you are drawing. All right, so are they triangles? Is it a triangle strip? Is it a line loop? Is it points? What are you drawing? Set it in draw arrays. And then basically the 2 parameters after that, where in the array are you starting and where are you ending? Everything we've done so far has been super trivial too, right? So if I've got, let's see, 6 points, so 1, 2, 3, 4, 5, 6, 0 to points.length is our primitives, right? If I change this to triangles, I would draw 2 triangles. What if I wanted to draw points and then I wanted to draw triangles? I need another call to gl.draw arrays with starting at points.length plus 1 to, you know, points.length plus triangles.length or something like that. Again, keep in mind gl.draw arrays is just going to spit out whatever you have in that buffer, and it's a 1D buffer. So if I've got points, and then I've got colors, and then I've got triangles, and then I've got colors, and then I've got a line loop, and then I've got colors, I need to index properly into that array. So make sure you're good with indexing. All right, we are going to end at this point, so let's get through this and then we'll call it a day. With our triangles, we are starting to get into the actual conceptual things here. Again, WebGL is only going to do triangles, points, and lines. Some gotchas. The edges cannot cross. They have to be simple triangles. They have to be convex triangles. And if you remember your convex versus concave definitions, here's my example. So this would be a concave shape. You can't have this as a triangle, right? This is basically something that's not going to work. It has to be a concave object that we're drawing. Triangles are great for that. Or sorry, it has to be a convex object. I said concave. So basically you have to have that. Your vertices should all be in the same planes as well. And then one of the other things, which may make you groan if you're coming from a more feature-rich world, your application is going to be in charge of tessellating things. And tessellating is going to be taking an object and breaking it up into triangles. And if you're coming from OpenGL, there is a built-in tessellator. We do not have access to that here. So you have to implement an algorithm yourself. And just to give you kind of a quick sneak peek at tessellation and triangulation, we'll get to that way later on, assuming that we don't go into the realm of Unity by that point. Effectively, what this is going to do is we're going to test for convexity. We're going to test for simplicity. And if those are violated, we need to start drawing triangles and we need to split things up. So here we've got a nice little dog or bear, depending on your perspective. You see it broken up into triangles. We have tessellated it. Now, there are a ton of algorithms out there for this. And interestingly, some of the more common ones are Delaunay triangulation. You may or may not have heard of that one. But it's basically the art of breaking things up into triangles as quickly as possible. This is basically getting into that notion that we don't want to have to do this by hand. All right, you see this object on the screen. I'm not hovering over it intentionally because it automatically draws points. But there's no way that I would ever want to set every single one of these vertices by hand. You'd go insane. What you want to do as the designer is draw the shape and let your application handle that triangulation by itself, right? So this particular algorithm that you see here, this is actually a very, very quick, which is surprising because this is in just raw JavaScript, not doing anything really nifty. But it's just going to automatically draw triangles, and this is drawing points based on where my mouse is and how quickly I move. So you can kind of see, look how blazing fast this is. I mean, this is real time. I'm not seeing any lag on my end. This is the kind of thing that a particular application would have to do before we send it to the shader. So I wish there was a nifty way to kind of play around with this shape, without having all this stuff here. But, you can kind of see, look at all these extra vertices I'm adding in. The application's tracking these vertices, then rendering it in the shader. But our choice of triangulation algorithm is going to be, how we actually render triangles to the screen. And if you see something like this, right, you could say, do whatever you want with all of your fragments and your vertices, however you want to track them, your application, update the colors in your Vertex shader. This is actually this is by somebody in the procedural generation community who has done, it's Red Blob Games, which I've been following his stuff for a while now. But he's done work on Realm of the Mad God, which I found kind of cool because that's been like crack for me for the past several years. But you get kind of cool stuff like this, where obviously here you're setting fragment colors and it's not nearly as pretty as the demo. But yeah. Alrighty, questions for today. Ah, and you can all see my note. All right. Other than that, class is over. Don't forget we have a lab due tonight. Let's see, so next time we will wrap up shaders and then we'll start talking about animation. Plan on having a in-class lab next week, so we will probably do, I assume we'll do a Zoom class for that, but unless you want to do Twitch and Discord voice chat, that's fine too. But it would basically be dead air the whole time unless if anybody has questions. But give you some more hands-on work with animation and playing with shaders and stuff like that. So what I'm going to do now is, let's see, so I think I will end the stream, but I'm going to stay in the chat just so that the recording will stop. I mean, I know we can click and record, but I hear there's supposed to be a concert in the Discord voice channel. So if anybody wants to pop in and hear that, it should be fun. Alrighty, have a great day. See you all on Thursday, and bye-bye.